compound interest and continuous compounding formula that we learned in section 3.1. And then we're also going to use our logarithmic properties that we learned in section 3.3 and 3.4. So we're just combining two things that we already know. So for examples 1 and 2, complete the table for a savings account in which interest is compounded continuously. These directions really should be changed because this is not compounded continuously. This is for n compoundings per year. So those directions are not exactly correct. Okay, so this first example, this is our formula for when we're doing n compounds per year. So it could be quarterly, monthly. In this case, we're doing monthly. So monthly means that our n value is going to be 12, right? We're going to compound it 12 times per year. Value. And then time to double. This is we're trying to find t. We'll double if our initial investment is 2,000, then that means that our a value is 4,000, right? We want to know when the final amount is 4,000. So that's what it means to double. And then amount after 10 years, we'll do that second. So let's plug in everything that we know. A is 4,000, P is 2,000. Our monthly rate is 1.5, but remember we need that as a decimal, so move the decimal to the left twice, and so that makes our R value 0.015. And then our N value we said is 12 since it's monthly. And we're trying to find T. We want to know how long it takes to double it. So let's plug all of those values in. So 4,000 equals our initial investment, 2,000, times 1 plus 0.015 for R over 12 raised to the 12 times T power. And now we're just solving this equation for T. So we've done a lot of work like this in the last two sections. So first thing we're going to do is divide this by 2,000 so that we can isolate the exponential part here. And we get 2 equals 1 plus 0.0, right? 5 over 12 raised to the 12t power. So we just isolated our exponential part. Now, anytime they're asking us for the time to double, this is always going to be double this. So when you divide, you're always going to get a 2 here. So you'll see this happen every single time. You'll get 2 equals and then the exponential part. So then we can take the natural log of both sides and bring down our exponent. So we get the natural log of 2 equals 12t times the natural log of what's in the parentheses.
We can't really see it.
Oh, sorry. Is it blurry?
Yeah.
It's really blurry?
It's kind of far away.
Okay, here. All right. Is it focused now?
No.
No?
Well, now it is. Yeah, it's good.
Okay. Okay. Let me know if that happens again. I don't know how to make my screen big, so I have I don't know how to make. Oh, I got it. Hang on. There we go. Okay, now I can see it. Okay, so our last step is to isolate t. So right now we have 12 times t times the natural log. So my inverse operation would be to divide. So we're going to divide by 12 and divide by this natural log. And then those cancel. If we do it to one side, we have to do it to the other side. And at this point, you guys might not even want to rewrite this. You can, but you could go straight to plugging it in your calculator at this point. Okay, I just squeezed that in there. Now, when you type it in your calculator, you need to put the denominator in parentheses. So we have the natural. Personally, I think if you have this shortcut, if your calculator is updated, it's very helpful because it's a lot less parentheses that you need to use. But if you don't have the shortcut, you have to put the denominator in parentheses. So 12 times the natural log of 1 plus, again, I'm going to use my fraction key, 0.015 divided by 12. Okay, so the fraction key is very helpful for problems like this instead of using a ton of different parentheses. And we get 46.9 We're going to round to 3 decimal places, so 239. And that's in years. So it would take 46.239 years to double our investment from $2,000 to $4,000. So it's kind of a long time for just $2,000. And then we want to know the amount after 10 years. So that means our t value is going to be 10. And we'll just plug that in. So we want to know what A is. So A equals our initial investment, 2,000, times 1 plus 0.015 divided by 12 raised to the 12 times t, which is in this case 10. And then here we just have to type this in. So 2,000 times 1 plus 0.015 divided by 12 raised to the 120th power. And we get 2,323.451. And that's dollars, so we can put a dollars sign on it. So $323.45 after 10 years. That's not too much over 10 years. But look at our rate, 1.5 monthly really isn't that high. So that makes sense that it's not growing super fast. All right, so that's our first example. Second example. Again, we are doing n compoundings per year. So you can see weekly, that means our n value is 52 weeks in a year. Yikes, 52. 52 weeks. So this one, we have 2 unknowns. If you ever don't have the rate, you have to find the rate before you're able to find the time to double. Because we need R in order to find T. So we're going to have to find the rate first here. So let's plug in what we do know. We know our initial investment is 300. We know our n value is 52 weeks in a year. And then we know when T is 10, our amount is 385.21. So that's our A value. All right, so let's plug all of those in. So 385.21 equals our initial amount of 300 times 1 plus, we're trying to find R. So R over N, which is 52, raised to the N times T. So 52 times 10. So we had to use this specific example so that we had these 2 values so that we can find R. So let's divide by 300 first so that we can isolate the exponential part. And we can actually type that in our calculator to get that decimal right away. And that is 1.284. And then we can multiply n times t. Okay, so now there are 2 different ways to do this problem. We could do it how we've always done it, where we take the natural log of both sides, we bring the exponent down, then we would divide by the exponent, then we would have to change the natural log to log base e, then we would have to swirl, then we'd have to subtract 1, and then we'd have to multiply by 52. Okay, that is a lot of work, but you could do it that way if you feel most comfortable that way. However, there is a shorter step that we can do. So whenever we take the natural log of both sides, we're usually, but that's not what we're trying to find here. This problem's a little different because we're trying to find R. So an easier step that we could do is raise both sides to the 1 over 520th power, because then that will just be 1. And so then we can raise this side again to the same, right? If you do it to one side, you have to do it to the other side. Keep your equation balanced. And we'll type that in our calculator. And actually, I'm going to grab the decimal. So we don't want to round. We want to use the whole decimal, because if you keep rounding, in the end, it could make, a big difference. So we'll take that. We'll raise it to the 1 over 520th power. And we get 1.00048. So just a 0 there. Equals 1 plus r divided by 52. And now we just have 2 more steps left. So again, you could do it the way that we've always done it. It just ends up being a lot more work in this case. But if you forget how to do it like this, then that's totally fine to do it the other way. So now we're going to subtract 1 from both sides, and that gives us 0.00048 equals r over 52. And our last step is to get r by itself by multiplying both sides by 52. So just times 52. And we get 0.025. So as a percent, that's going to be 2.5%. So again, anytime you're missing r, you need to find r first. Now we can find the time that it took to double. So we're looking for t here, and the time is 600 because we started with 300. So we'll plug those numbers in. So a is 600 equals our initial investment of 300 times 1 plus. Now we know r, and since we're plugging it in, we need it as a decimal, so that's 0.025 over 52 raised to the 52t power. Like I said on the last example, anytime you're trying to find the time it took to double, right, we end up dividing by, this is always going to be 2. So you can feel free to just start with that step if you would like to. And now we have our exponential part isolated, which means that we can take the natural log of both sides. So natural log is going to be easier here because we're trying to find a variable in the exponent. So we'll take the natural log, we'll bring the exponent down, and we get the natural log of 2 equals 52t times the natural log of everything in our parentheses. And last step is to isolate t. So right now we have all of them being multiplied. So we're going to divide. Okay, I don't have a ton of room to write this, so I'm just going to do that, and we'll plug that in our calculator. So again, fraction key is really helpful so that you don't have to put as many parentheses. So we'll divide by 52 times the natural log of 1 plus 0.025 over 52. If you don't have the fraction key and you have an older calculator, then you're going to have to make sure that you put the denominator in parentheses. Okay? Otherwise, your calculator is going to divide by 52 and then multiply, and we don't want that. So 3 years. So not as long. Right now our annual rate was 2.5%, so it was a little bit higher. So it didn't take as long to double, which is good in a real life scenario. Any questions on this problem? Okay, so again, it's just combining two things that we already know how to do. We did kind of have a little bit of a new strategy here, but like I said, you could always use the old strategy. It's just a lot more steps to do it that way. On your homework, There's none in the notes, but on your homework, which I'll show you in a little bit, there are going to be some problems that are the continuous compounding ones. So the a equals pe to the rt power. It's the same process though, but it's really nice because when we end up taking the natural log of both sides, the natural log of e is just going to cancel. So those problems are actually a little bit easier. So there will be some of those on the homework. All right, continuous decay. So this is our half-life formula. We looked at this on one example in our notes. So complete the table for the radioactive isotope. So we have our half-life. So HL here stands for half-life. T stands for the time. And then amount after 1,000 years. So that means in this case, T is going to be 1,000. And we want to know what the amount is. So A sub F stands for amount final, and A sub O stands for initial amount. Okay, so our initial quantity is 10 grams. So this is our A sub O. We're trying to find A sub F, our final amount, and T is after 1,000 years, and this is our half-life, HL. Okay, so let's plug those in. Amount final. Our T is 1,000 divided by the half-life, which is 1599. And then we just type that in our calculator. So 10 times 0.5 raised to the 1,000 divided by 1,599. And we get 6.482 grams. That makes sense. I always compare my answer in terms of what numbers were given just to make sure. So we started with 10 grams and the half-life is after 1,599. So that would be 5 grams after 1,599. And we wanted to know 1,000. So that's not going to take as long, which makes sense why it's 6.482. Right? So just compare 1,000 to the half-life and 10 to our grams, and that does make sense. Okay. And one more. So our half-life is 24,100. We don't know our initial quantity, so we're trying to find A sub O here. Our amount after 1,000 years, so T is going to be 1,000, and 0.4 is going to be our A sub F, our final amount. So let's plug those in. So 0.4 equals, we're trying to find A sub O, the initial amount, times 1/2 raised to the 1,000 over 24,100. So we have a little bit of work to do here. Well, actually, this is just a number, and we're trying to get A sub O by itself. So all we have to do is divide by this number. If you wanted to simplify this to 10 over 241, you could. Might be just a little easier to type in your calculator. Correctly, then you're going to get the problem wrong. So let's type this in. 0.4 divided by 1/2 raised to the 1,000 divided by 24,100. Oh, I put in a negative instead of a decimal, so let's change this to a 0.4. There we go. 0.412. And that's in grams. So we want to make sure we put our units as well. So initial quantity 0.412 grams. So for all these problems, you just need to plug in what you know into the formula and then use what we've learned in this chapter to solve for your unknown. All right. So where would we use logarithms in real life, right? Why does this stuff matter? Our book gives a lot of real life examples, so I just picked one. The Richter scale, which is used to find the intensity of earthquakes, is one example of using logarithms. So this is where you would see logarithms in the real world. Maybe not used specifically, but this is where they're used. They are used. Okay, there's a lot more math than you would think. So let's see. I sub O is 1. So we're going to plug a 1 in here. And then I is the intensity. So Santa Cruz Islands in 2006, on the Richter scale, that was a 6.1 earthquake. So let's plug this in. For R, that's 6.1 equals log base 10 of I over 1. So we're just going to, so that's just I. Okay, well, we want to know what exponent changes 10 into I. That exponent is 6.1. So just using the definition of a log, we can swirl this, right? 6.1 is the exponent. So if we type that in our calculator, we get 1258925.412. And that is the intensity of our earthquake. Okay? And we're going to compare. Once we finish these other two, we'll compare them. So we're going to do the exact same process when we plug in 7.6 here. So really what we're doing is doing 10 raised to the 7.6 power. All right, so let's plug that in our calculator. And that's 3981017.06. So I'm going to put some commas in there just so we can see how big that really is. So if you look what happened from a 6.1 to a 7.6 earthquake, look what happened to the number. That's almost 30 times stronger. So when you hear 6.1 versus a 7.6 earthquake, it really doesn't sound like it's that big of a difference, but it actually really is. So that's why it's important to really understand what's happening with the Richter scale. So now a 9.0 earthquake, I think this is going to say northern. So we have 10 to the 9.0 power, again, just following the same process. And that is going to be really big. Yep, 1 with 9 zeros. So look at what happened from a 7.6 to a 9.0. That's almost 25 times as strong. So the Richter scale, even a little bit of a difference really makes a big difference for the intensity of the earthquake. Okay, so that's why it's important to really understand what logarithms are, because it does make a difference. All right, so here's one data in decibels with an intensity I is given by this. So 10 log base 10 of I over I sub 0, where I sub 0, the initial intensity, is an intensity of 10 to the negative 12 watt per square meter, which is the faintest sound heard by the human ear. So find beta. Okay. So beta equals 10 log base 10. I is 10 to the negative 4th power in this example. And then I sub 0, they said, is 10 to the negative 12th power. Okay, and this is the intensity of a door slamming. So let's simplify this. That's really 10 to the positive 12th over 10 to the 4th power. So if you subtract those, we get 10 to the 8th power. And so now we have 10 times log base 10 of 10 to the 8th. And using our definition of a logarithm, what exponent changes the base 10 into the argument 10 to the 8th? And that would be the 8th. That would be the exponent would be 8. 10 to the 8th power would give us 10 to the 8th power. So this is just 8. So now we have 10 times 8, which is 80 decibels. Okay, so a door slamming, the intensity is 80 decibels. And now we're going to do the same thing with the intensity of a loud car horn. So again, 10 log base 10 of 10 to the negative 3rd over 10 to the negative 12th. And if we simplify that, that's 12 over 3, so that's 10 to the 9th power. And then we know that our log is just the exponent that turns the base into the argument. And that's 9, right? 10 decibels. And the last one, so we have 10 to the negative second over 10 to the negative 12. So negative 2 minus a negative 12 is 10 to the 10th power. So we're just asking what exponent changes 10 into 10 to the 10th, and that would be 10. So 10 times 10 is 100 decibels. So if you look, a door slamming is 80 decibels, a loud car horn is 90 decibels, and a siren at 30 meters is 100 decibels. 80, 90 to 100 doesn't really sound like that big of a difference, but these sounds are all very different. So that's why our logarithmic using logarithms actually helps us understand what's going on. Okay, so there's some real life examples. I have one more example. Find the exponential model y equals a times e to the bx power that fits the points shown in the graph. So we have a y-intercept, 0 and 1, and then we have an xy point, 4, 5. So we're first going to use our y-intercept, right? X is 0, y is 1, and we're going to plug those in for x and y. So y is 1 equals a times e to the b times x, which is 0. So e to the 0 power, e to the 0 power is just 1. So we have a times 1, which means that a just equals 1. Now that we know what a is, now we can use this point to write our equation. So value that we just found of 1 times e raised to the b times x. So this is going to help us find b so that we can write our equation. So 5 equals e to the 4b power. And now we're going to use what we learned in section 3.4. We can take the natural log of both sides and bring the exponent down. And the natural log of e, that cancels, so we just get natural log of 5 equals 4b. Divide both sides by 4. We type that in our calculator, and we get 0.402. So we'll just round that to point. Well, actually, we can leave that. We'll leave it 3 decimal places. So now we need to write the equation. Y equals my a value of 1, so I'm not going to write 1 there. E to the b x power. So this is the equation of our exponential model for any x, y point. So we just used the y-intercept to help us find a, and we use this point to help us find b, and then we can plug in a and b to get our model. Oops, sorry. I just couldn't see that. There we go. And that's it. So I have a couple things that I want you to correct on your homework. So let me pull that up. Okay, so this front page, I put the models here so you can see what the original one looks like. So here you're going to match these with these. There are some transformations, but I think there's one of each. So you should be able to look up here and compare. Like here's that matches A. So then that should help you. You should look and match that with one of these equations. So these are meant to help you answer this question. So then here, this is updated, so I can't remember what yours said, but this first one is compounded monthly, so we should have, I think that formula is written there. but I think for 15, it still has this formula, but this for 15, we're going to do compounded continuously. So scratch out that formula and write the P times e to the RT power. So this is continuous compounding. Okay, so again, it's the same process as what we did in the notes. And then for number 17, I think you already have this equation there. So that one should be good. But for number 18, again, I want you to change this to compounding continuously. So cross out the equation that's there and put A equals P to the RT power. And then half-life is good. There's 2 of these, like the last one that we just did, and then one word problem. So that's your homework for tonight. There is a key on Google Classroom, and we will grade, or so you guys will just hold on to it. Please grade it. Please treat it like a normal homework assignment. Obviously, you need practice for